All right, line A6, learning task 1 features field effect transistors and insulated gate bipolar transistors, IGBTs and FETs. We're going to start by talking about the field effect transistor. The field effect transistor is going to be used in a similar way to what we learned in first and second year with our bipolar junction transistors. Bipolar junction transistors, or BJTs, you should be familiar with these. If not, you should have also gone through that first video that I posted on this whole subject, but you should have some familiarity with, this device here, where we've got a base, and the amount of base current flowing through here is going to go and give me the total amount of collector to emitter current that I'm going to go and get through, depending upon the type that I am going to go and have. PNP in that case there. Those ones were going to be controlled by current, the amount of current that was going to go and flow inside of the base. The problem with that is that when you've got a device that has got hundreds of thousands, if not millions of transistors that are going to be inside there, all of that base current goes and adds up. Take a look at your phone, your computer, tablet, anything like that. These all run off of small switches, transistors that are just making decisions in the background, and there's going to be millions of them. If your phone had to go and use BJTs to do all of that switching, you'd have a battery life of, maybe 1 or 2 hours tops before you'd be charging that thing again. So we don't like that. Rather, we want to have something that's not going to waste current on base current. So we have moved to the field effect transistors. Field effect transistors are going to be different in that they have got two main things. One is going to be a unipolar. This means that they are going to go and have all of the current that is going to go and travel through my one region. It's either going to be P or it's going to go and be my N type of material that I'm going to go and have, compared to my BJTs where I would cross over those depletion regions, P and N types of regions over there. The other one is going to go and be that it is going to be voltage sensitive. They are going to be controlled by voltage, not by current. And the FETs are going to be used as well because the FETs have got this beautiful thing where my gate current, my control current, is going to be a impedance that is really, really high. Okay, the way the book talks about it over here says that they've got a high input impedance. We're not talking about the impedance that's going to go across the main run. We're talking about the gate impedance. The gate impedance is going to be very, very high, which means that the amount of gate current, there's always going to be a tiny little bit of leakage gate current. My IG is going to be very, very, very small off of these things. The first one that we're looking at is this JFET over here, the junction field effect transistor. And the way that the JFET works is that we are going to go and have a bar of material. Now, I don't know if you remember your formula for determining the resistance of a device, but R is equal to K times L over top of CMA. This tells you the resistance of any type of a device, and we know that the CMA is going to be the area. We know that the L is going to be the length, and we know that the K is going to be the material type. And we actually need to go and refer to this to understand how these operate. Material type, the length of the material, and the circular mill area. This is going to go and be a channel that we are going to go through. We've got an N-type channel that we are going to have over here. It says N-type of channel, which means that this thing is going to go and be pentavalently doped. Remember, there's an N in pentavalently. So it's got an excess of electrons inside there that we are going to go and have. That N type of channel is going to go and carry the current through, but what we're actually going to do is we're going to go and affect how big. We're really going to go and affect this over here, which is going to be my circular mill area, and we're going to affect that circular mill area in this area right over here. We do have 3 leads as well. We've got them that are going to be called our source, our drain, and our gates that we are going to go and have. How do these things actually go and operate? Well, I'm going to go and draw on this one over here. We're going to see it a little bit later on as well, but basically what we are going to do is we're going to set up depletion regions. You have to be familiar with depletion regions to understand what's going on, but there's going to be a depletion region around here where we've got this P to N type of material. And there's going to be a depletion region that's going to be over here where we've got this P to N type of material junction as well, which means that if I take a look at it, I'm very, very limited as to the size of that channel that I have in between there. And because that channel is actually going to be my circular mill area, the area that I have to go through it, If I go and increase the size of the depletion region, it's going to go and choke down that channel. And if I decrease the size of the depletion region, it is going to go and let up on that channel. It's going to increase the size of the channel, and that is going to go and change this whole formula. We choke down the CMA, we're going to go and have a greater amount of resistance. We're going to have to be dropping more volts, pushing our electrons across. And if we go and open up that channel, our CMA is going to go up, which would mean our resistance would go down, which would mean that we would drop less volts over top of the JFET over here. This is all happening through that channel. We've got some standardized designs for these things, N channel and P channel type, where we're going to go and have source, drain, and gate. And if I take a look, we always say that when it comes to semiconductors, the bar is going to go and be my N type of material. If we were looking at a diode, we said that it was going to be, this was going to be my N type of material, my negative or my cathode end. We see that with the bar over here. We see the bar as well. We see that arrowhead on the P type. The arrowhead is on that P type. If you take a look at my N channel type over here and take a look at this one over here, let me just remove all of my scribbles. Looking at this one, you see that we have got a N channel, so the main part of it is made out of N, and that my P regions, these two over here, are going to be my gate. Refer that to these ones over here. I see that my gate is identified as being a P with the arrowhead, and that these are just going to be identified as they're part of the bar there. Therefore, they have to be an N channel. Arrowhead always points towards the N. This one over here, the arrowhead is pointing out, which means that the gate must be my N type of material, and which would mean that this would then have to be a P type of channel. They look very similar. The drain and the source, sometimes we're going to go and have symmetrical ones where we can interchange. We can go and run current in on either one. Other times we're going to go and have asymmetrical, but usually what we're going to do is we're going to go and have the drain, which is going to be the positive, and the source, which is going to be the negative. And just look at this as being, what is the drain? The drain is going to be connected to positive. Positive is a pile of holes. Remember, go back to the battery analogy that was in the first review video. Positives are going to be a whole pile of holes. And then my source is going to go and be a pile of electrons over here. So we're going to take those electrons and we're just going to drain them, just like draining a basket, into those holes over there. So drain, positive, is the standard convention that we are going to go and have, and then source being my negative. For all of my JFETs, we are going to go and connect the gate in a reverse bias. Now, this is going to be very, very important that we're going to connect them inside of a reverse bias, because that's what's going to go and clamp down on that channel that we are going to go and have. Going back to this one over here, let me just erase a bunch of stuff. And we're going to affect that CMA. We know that for any type of a P and an N type of junction, and we're just going to go and draw this maybe, actually, yeah, why don't I just move this one a little bit over here to the, oh my goodness, undo that. It wants to recenter it there. It still wants to recenter it. Whatever, I'll move this all the way down, and we'll draw up top over here. I'm just going to draw this thing out a little bit larger so we can actually see what's happening inside this channel. We're going to start with our 2 blocks of P type of material over here. P type of material, and then we're going to go and have our N substrate that is going to go and be my drain and my source that we are going to go and have. So source, drain over here. We know that from what we just talked about, we're going to go and connect these things so that I'm going to go and have a positive over here connected towards my drain and a negative connected towards my source. So this is my wiring over here, and this is my wiring over here. If you take a look at that, do I have a complete path for current flow? Why, yes, I do have a complete path for current flow. If you take a look at it, I'm going to be able to take those electrons and I'm going to go and be able to run them through this semiconductor. Remember, it is semiconductor, which means it does still conduct. It's not our best conductor out there, but it's still a pretty dang decent conductor, and especially once we go and dope it, give it either holes or electrons to go and act as our current carriers. So I'm going to go and have current flow that can go right through this channel over here. The next thing that I'm going to go and do is I'm now going to go and take a look at that gate that I'm going to have. So I'm just going to remove that channel over there. We're going to take a look at our gate. Now, if I were to go and positively go and connect, or if I were to forward bias a gate, I would have to go and put a positive to my P and a negative to my N, which is what this whole entire channel is made up of. I'm just going to put a big N in the middle over there. What we have is we have got a depletion region that is going to go and be around each of these. And depletion region is where my N and my P type materials have combined together to go and form a small barrier potential. And that small barrier potential is going to basically balance out my semiconductor. So there's no available current carriers. All of my holes are going to be filled by excess electrons inside of there. So those areas basically become a no-fly zone for my electrons traveling through here. If we have a no-fly zone for those electrons, we're not going to get anything happening through there. So yeah, we basically have narrowed down our available area for us to go and travel through here as being this narrow little channel over here, which is going to be our circular mill area here. If I take this now and I reverse bias, so I'm going to go and take a negative over here, and I'm going to go and attach this thing to my N type of material. Well, if I've got a negative, that means I've got an excess of electrons inside of here. Those electrons are really going to go and fill the holes in my P type of material, right? So we've got some holes inside there. We're going to get electrons that are going to go and flow into here. There's going to be a small amount of initial current flow just to go and set up these depletion regions. As they do that, they're going to go and increase the size of that depletion region. Now, what we referred to inside of that review video, you cannot blow up just one side of a balloon. So if I'm going to go and affect the depletion region over here, for every action there's an equal and opposite reaction, which means it's also going to go and affect the depletion region all the way around this. And what we see is that we are getting a closing down effect. As I increase the amount that I am biasing against here, the more that I'm closing this down, which means the more that I am dropping that circular mill area. And as the circular mill area goes down, the resistance goes up. So I can drop more voltage then across from this end over to this end, particularly if I had another load, connected in line with this. We'll take a look at that in a second. We're going to talk real quick about some other constructions that we have off of these things, and then we're going to go and put them into a circuit. The other one that we still have to talk about is going to be for my MOSFET. So the JFET was the junction field effect transistor where my P and my N type of material actually touch each other. The other one that I'm going to go and have is my MOSFET. And the MOSFET is going to go and have silicon dioxide, Si2, that is going to go and insulate my gate and my semiconductor channel. So it is going to be an additional layer of insulation in between my gate and then my source and my drain over here, which means that I'm going to go and have even less leakage current that I'm going to be able to go and pass through this thing, which once again means I'm going to go and have a better overall device when it comes to my total amount of losses. We want to cut down the total amount of losses because that's how we go and get efficiency out of our electronics. This is going to be my MOSFET over here. They show the silicon dioxide insulating layer over here. We see that we've got our source and our drain, so we're still going to pass current through from here, from my source to my drain. How does that actually work? Well, what's happening inside of my insulating layer over here is that we're still going to go and have distortion of my orbitals inside of there. I don't know if you remember taking a look at caps inside of your second year, but caps were made where we have electrons that are going to be going around our central nucleus. And then we say if we go and place a negative and a positive charge by it, that's going to go and change my overall. The positive is going to repel the nucleus, which is a positive center. The negative is going to go and repel the electron, which is a negative. And the positive is going to attract that same electron that's being repelled away from the top. The negative is going to attract that same nucleus up there, and we end up with this distortion that's going to happen where my nuclei move up and my electrons move down, and we end up with this overall different look that is going to be something like this. Distorted orbitals. And those distorted orbitals now means that there's going to be more positivity at this end than there's going to be at this end. We get the same thing here with this gate. The gate is going to go and use this insulating layer over here, which is relatively easy to distort. It is going to go and use that to go and push a little bit of positivity, a little bit of negativity over here, which is then going to allow us to affect it, but it still gives us blocking of any type of leakage current. Sometimes they will be called IGFET, insulated gate field effect transistors, but it's usually known as MOSFETs, metal oxide semiconductors. They sometimes will have a fourth lead as well called the substrate, and it's really just going to be what we're building this thing on. That's this section right over here. If we do have them, we're going to go and connect those substrates as well. They're designed to just kind of act as our base, our ground, and we need to go and have them. So we're going to go, sorry, I shouldn't say ground as our reference. We're going to go and connect them to the same potential as whatever we've got our source. So if our source is going to be negative, we would connect our substrate to a negative. If our source would be positive, we would connect our substrate to the positive, etc. We do have a couple of different ways that we can control these things as well. We've got enhancement and depletion. These are a lot more of, electronic type of things than what you're probably going to have to ever deal with as an electrician. But if we have got depletion modes versus enhancement modes are going to go and allow me to increase the size of a channel. So I can go and start with a channel that's a certain size, and I can basically drop the depletion region, which is going to go and enhance that channel, make it bigger. Depletion mode means that I start with a channel and I can only make that channel smaller, and I'm actually going to have a couple of them that I can operate in either enhancement or depletion, which makes them very handy for semiconductor applications, because I can either go and throw a gate wide open or I can completely close it off for the most part. FETs that have a reverse bias for the gate usually are going to be depletion mode. The module says that it's always, but it's a usual thing because it depletes the size of the channel. And they're like having, they give you this example, a normally closed switch. And then enhancement ones, we're going to go and increase the gate bias, which is going to go and increase the effective size of the channel. Basically, we're bringing the gate closer to breaking over that PN junction. So we can go and have a normally open switch that can be closed. Yeah, we're not really going to go into those things for which one we're going to be using for enhancement depletion, because that's a lot more of a power electronics. There's very good money to be made in industrial electronics, big power rectifiers and things like that. Example, my brother's company there, he works out in North Van at a large chemical manufacturing plant, and they had to bring in a rectifier specialist, and it was a $18,000 bill for this guy to come out for 3 days. You only got to do a couple of those jobs in a month, to go and make your six-figure income out in a year. But he knows his stuff inside and out, and in those industrial semiconductors, when you're dealing with large, high-voltage components, this is a multi-million-dollar operation. It pays to know that stuff. But for most of you, probably not going to jump into a lot of these. These are my standard symbols here for my MOSFETs. If you take a look at this, the big thing I want to go and note is that my gate is insulated. It doesn't actually make connection with the actual channel. The channel is going to be that source and drain that we have going across there. The gate does not go and make any connection to it, and I've got an arrowhead that points always towards the ends. The arrowhead points towards the end, therefore the channel must be N. The arrowhead points out of the channel, therefore the channel must be P for this one over here. MOSFETs are great because of this insulated gate. We have almost no leakage current. I gate is going to be tiny, tiny, tiny that we are going to go and have. Which means that if you've got MOSFETs inside of your battery-powered electronics, you're going to have very low amount of losses. That's what your phones are going to go and use, is going to be variations of FETs. Low noise and high frequency amplification is possible with them. Means that they're not picking up a lot of garbage that they shouldn't be. High frequency means that they can go and switch back and forth really, really quickly, switch on and switch off. But they do have some, major disadvantages in the fact that they're super sensitive. Static charges, electricity that you're going to pick up by the way that you walk around, shuffle your feet, etc., can go and destroy these things as you touch them. So you got to be real careful about grounding on these things, and that you are maintaining a ground on yourself with a ground strap, etc. Read through those points that they show you inside of your binder, and just be very careful when you're handling anything that is a FET, because they are so sensitive. We're going to talk over here about JFET amplification. And to do that, you have to still be familiar with your BJT amplification. BJT amplification is really just looking at my values of resistance. Let's start the examination of this by looking at the central component over here, which is going to be that JFET. And I want us to just go back to the very basics that we looked at over here, which was that a JFET is nothing more than a chunk of semiconductor that is going to go and have a circular mill area, CMA, that is going to go and be variable. Which means that really if I look at something as being a semiconducting chunk, that's something with resistance, that's got variable CMA, it really means this thing is simply a variable resistor for the effect of what we are trying to go and do over here. So I'm just going to go and draw this out as being a variable resistor just real quick, and then we're going to go into the actual analysis of this. First thing I'm going to do is I'm going to go and have just 3 resistors that I'm going to go and place in here like this, okay? And I'm going to go and say that this is going to be my positive voltage over here. I'm going to call this one RD because it is simply just going to go and be the same drain one that we have over here. I'm going to call this one RS because it's going to be simply the same source resistor that I'm going to go and have. And then I'm going to go and have this one over here, which is going to go and stand in for my JFET, okay? So I'm just going to call this thing JFET, RJFET. And remember, we said that we can just control the amount of resistance that's going to go and happen inside of this thing to go and control the amount of output voltage that we're going to see. If I take a look, I see that my output over here, my V out, is being measured from this point here in relationship to my ground. So that's what we're going to be measuring inside here. Let's give ourselves a really simple voltage to go and work with. We're going to go and say that we're connecting this thing to 60 volts over here. And I'm just going to do that off of this one. We're going to say that to begin with, we are going to go and start with each of these ones here at 20 ohms of resistance. Let's say 20 ohms, 20 ohms. And let's say that the resistance of the JFET was currently at 20 ohms. If I had 20 ohms of resistance for each one of these, I would have 60 ohms total as a series circuit. Therefore, I would be dropping, a volt an ohm. Which would mean that if I were to go up from the bottom over here, I would see that I'm going to be dropping 20 volts over here and 20 volts over here. I is equal to V over R, 60 volts over 60 ohms, 1 amp of current. So 1 amp times 20 ohms drops 20 volts here, another 20 volts here. Right now, I would see a value of 40 volts that I would have out at that terminal. But if I were to go and change this value here, so if I were to adjust my JFET, and we'll talk about the adjustment in a minute, but if I were to go and change that value and bring this thing to, let me just think here for a second. Let's take this thing down to 10 ohms, okay? We'll take it down to 5 ohms would work better, actually. 5 ohms. If I were to take this down to 5 ohms, so I'm going to adjust this thing, that would be that little arm sliding up there. Now I'm going to go and see a differing value of voltage that's going to come out over here. And we would be able to figure that out by saying, well, 20 plus another 5 gets me 45. I is equal to my V or E over top of R. So if I were to take 60 over 45, let's do that one real quick there. Let's start this calculator. 60 divided by 45 gets me to 1.3 amps of current that I'm going to go and have traveling through from top to bottom. Over here I say I've got 25 ohms. So if I were going to take that 1.3 and multiply it by the 25 ohms of the JFET combined with my source, so times 25, I come out to a value that I would be now at 33.3 volts to that top over here. So 33 volts that we would have over here. Perfect. So we see that adjusting this is going to adjust the amount of voltage that we are going to go and have on our output. Well, how does that actually go and work inside of here? Well, I'm just going to erase all of this and let's go and take a look. Okay. Going back into this one over here, we've got that same drain resistance, source resistance, and then I have got the actual JFET itself. I'm going to go and have a gate resistor over here because remember, there's no complete path through over here. There's absolutely no way that I can go and send anything through because this is going to be a PN junction. There's going to be a depletion region inside there. So I need to go and have something else, that's this gate resistance, so anything that I send in is going to be able to go and travel through. I also have got these two funny looking things over here, which are going to be my capacitors. And capacitors will go and pass AC values. They will block DC values. So as long as I've got a changing value of voltage on my input over here, I'm going to be able to go and pass that changing value of voltage through here. I'm also going to go and have changing values of voltage that I'm going to be able to go and pass out of here. And so we're going to go and see, up downs that are going to go and happen as a result. So I'm going to start with this thing bias probably somewhere midpoint to my supply value of voltage. And then I'm going to go and take in a little bit of AC volts. Let's do that right over here. So over here, I see that I have got an increase in my value of volts that is going up. So my volts are climbing up. As this volts becomes more and more positive, we are going to go and have more and more current that is going to be traveling through here, right? We've got this more positivity. Therefore, we're going to have more current that is going to travel through here. The electrons are going to go and do. Then they accumulate on this plate. As they do, they drive electrons away. For every action, there's an equal and opposite reaction. So I'm going to be driving electrons away from this one back towards that source. And this is just the way that this current is going to be flowing. If I then go and take a look at what that does over here, I see that because I'm increasing the amount of current through here, therefore V is equal to I times R. As my current goes up, I'm going to go and see more volts across here. So this voltage over here is going to go up. And as that voltage goes up, it is going to go and change what happens over here. Well, we've got an N type of channel over here. We've got a P type of material that I'm going to go and have over here, right? That's what my gate is going to be. And if I were to draw this thing, let's just actually do that. Yeah, draw like that. It's my N type of channel that I'm going to go and have. We've got our two little P-type blocks that are going to be in right over here. And we've got that depletion region that's going to be just around the outside of these. Okay? So I've got all of that laid out here right now, and then we said that we increased the value of positive voltage that we had applied to this section over here, which is going to go and be my P-type of material. P-type of material, P-type of material. As I increase my voltage applied to a P-type of material, I'm going to go and see my depletion region get smaller. So really, this depletion region is going to, come on, it's not wanting to erase it right now. Oh, there we go. That depletion region is going to go and get smaller, which means that I'm going to go and open up this channel. Okay, so we've opened up the channel, which means my CMA has gone up, which means that my resistance for this has gone down. So now I'm going to go and have less resistance that is going to be made up of this chunk over here, my actual JFET, which means that if I have got less resistance on this side, I'm going to go and drop more voltage on this side. So I'm going to actually see a decrease on my output side of these ones. How does that actually look? Well, we could just start by saying that, during my initial biasing, maybe before we applied this value of voltage, that we had a value of, we're going to go up here, we're going to call this thing 60 volts. We'll say that this one was 15 ohms. We're going to go and say that this one over here was 5 ohms, and we can say that this one initially was 10 ohms. But we opened up that channel, which means that this 10 ohms is now going to go and drop, and if we would go and drop that 10 ohms, we are going to go and lose resistance inside of here. So this resistance will drop. As that resistance drops, I still have to drop the whole 60 volts over top of this. I don't know if you remember your voltage divisor formula, but that was that your V over top of anything is going to, so we'll call that Vx is equal to Rx over top of RT times Vs. Source voltage. We still have 60 volts as our source voltage. We are now going to go and take a look, and we say if this thing drops, let's drop this thing all the way down to 2 ohms, okay? If it were to drop down to 2 ohms, our sum of this total channel here would now become 22 for our RT, 22. And my Rx, if I wanted to find out how many volts I'm going to be dropping across here, would be then 15. So we're going to have 15 over 22 times, this is going to be a value of 60 over here. 15 divided by 22 times 60 gets me to a value of 40 volts. And so all of a sudden, I'm going to be dropping over top of this resistor 40 volts. Before, I was only dropping 30 volts over top of it. Now I'm dropping 40 volts over top of it. So before, this line over here was biased at 15 volts. Now this thing has dropped all the way down from that 15 volts. It has dropped all the way down to 20 volts. Wait a minute. I did that. That wasn't 15 volts. It was at 30 volts. That's what I did. It was at 30 volts because half and half was 30 volts. Now it will be dropping down to 20 volts. And we see that on our output over here, that this thing is going to be dropping down to 20 volts. Really, really handy for us when we take a look at all of these, because what we see happening, I'm just going to erase all of this now that we've gone through this math once, is that as my voltage goes up, oh my goodness, what happened over here? 2 seconds. Back to where we were there, I don't know, it's glitchy. But as we see here, as my voltage goes up on my input, I'm going to go and see it going down on my output. But I see it's going to be a much larger value because now I'm taking it out of 60 volts. What I might have coming in here might be a 0, to 5 volt type of signal that I'm going to go and have. That 0 to 5 volt signal, I'm then going to be able to make it much stronger so it comes out over here. This is just called amplification. We use amplification for all sorts of stuff. We're going to take in a lot of small, weak signals in industrial control, stuff that is going to tell us about positions and temperatures and things like that. And then we are going to need to go and amplify them so we can go and take them to usable values that we can use to go and drive, gate valves and all sorts of other components inside of here. We see that overall, my FET has operated very similar to what we saw inside of BJT amplification. If you remember that at all from your second year, you probably don't, but maybe go back and take a look. BJT amplification operated the same way, except the BJT had this issue where I had to actually be running current through from my emitter to my base. My base to emitter always was carrying current, and because it was always carrying large amounts of current for me to be able to do my emitter to collector current like that, I always had heat coming off of those things, off of the actual BJTs. We don't want that, so we can get rid of that. This path that we see over here, this resistor, can be very high, hundreds of K ohms and more. So we're going to only have a tiny, tiny amount of volt of current that's going to travel through it. We do need that complete path. We will have a tiny, tiny bit that's going to go through, but it's nowhere going to be near the same as what I had on my BJTs. Just remember that for our gates on our FETs, we just have to keep everything reverse biased, and that it's all just being threatened with voltage. We're just increasing and decreasing the size of that depletion region, but we're never actually breaking it over. Okay, next section that we got to go and take a look at here is going to be my IGBT, and IGBTs are much more common these days than they were, probably even just 5 years ago. It's an insulated gate bipolar transistor, and it's a 3-terminal semiconductor device, similar to what we had for our FETs, but now it's going to be made with a few more layers. It has kind of a best of both cases situation. Extremely fast switching with super high efficiency, and we have got 4 alternating layers now, NP, NP, that we are going to go and have. And then we're going to go and control them with an insulated gate that we're going to go and have up top over here. So looking at this over here, I'm going to go and have my collector, I'm going to go and have my emitter that I'm going to go and have over here, and I'm going to go and have my gate over here. Ultimately, what we're trying to do is we are trying to go and get current going through from my collector to my emitter. If you take a look at this, we see that we've got a P and an N junction over here. So this is going to go and have a depletion region. And we also see that we are going to go and have a P and an N type of junction that is going to go and be over here. We've got an N type of region and another N and a P type of region over here as well. Disregard this side over here. They're just connected internally back and around to these. But what I'm going to be able to go and do with this is I'm going to be able to go and once again through my insulation, that's going to be this set of layers that we're going to go and have over here around there. I'm going to be able to distort the orbitals on that insulation. As I distort the orbitals on that insulation, I'm going to go and start to allow this depletion region to drop down. As this depletion region drops down, it is also going to go and cause this depletion region to go and drop down. Do note that we've got a N negative and an N positive. This just means that this one is more negative. It's got more pentavalent doping inside of it, the epitaxial drift region. This one's just got less doping inside of it, and they do need to have two of these that are going to be separate so that they can go and control each of these two sides more or less independently that we're going to go and have. It's got an incredible current gain, far greater than what we would have off of our BJTs. So we're going to have a little bit of current through there, but we don't have as high of a gate current, and we get super fast switching and high voltage operation. Because we've got all of these insulating layers over here, we can operate this thing at a much greater emitter to collector type of voltage because we've got doubling up of our layers of insulation inside of here. It is a voltage controlled device. I do have that insulation that is going to be in there. Note how the gate is insulated. It's shown as being separate off of these ones. But note that the way that we draw it here for an N channel and a P channel is very similar to my type of to my BJTs that I'm going to go and have. We have these, drawn here on angles, etc. Voltage controlled devices, meaning we don't have to go and put current through them. There will be a tiny little bit, as with all semiconductors, there will always be a little bit of leakage current, but it's mostly voltage controlled. It does have forward blocking operation. That's going to be similar to the MOSFET, where we're just going to go and throttle down the channel, but it has far lower I squared R power losses for a given current than a comparable MOSFET. If I take a look at my MOSFETs, all the way up top here. Here's my actual MOSFET. I'm going to actually dissipate a fair amount of heat as I'm traveling through that channel back and forth over there because I don't have complementary. It's a unipolar type that I have over here where it's only traveling through the N type of material. As soon as I go through P and N types of materials simultaneously, I actually gain the ability to conduct with fewer losses because I'm going to be basically feeding into my P-type material and then taking electrons from my Ns, combining them across here, feeding back in. So we're just kind of pumping stuff through instead of just pushing stuff through from one end to the other. They also have got a much lower on type of resistance. When they're actually turned on, the amount of resistance that I see measured across from here to here are on is much lower than what I had across that channel of the FET. So because they can handle high amounts of currents, high amounts of voltages, and because we can go and switch very, very quickly with them, we are going to go and use these things in a lot of our higher power type of applications. They give us a comparison chart over here, for IGBTs, MOSFETs, and BJTs. Don't bother memorizing it, just, kind of get a feel for these things. If you take a look at your voltage ratings, we can go up to 1,000 volts off of these things. And my MOSFETs and my BJTs, we're not going to be able to reach those same types over there. Current ratings, I can go to some very, very high current ratings on all of them. Depends upon the type, as we go to high amounts of current. My input, small amounts, 4 to 8 volts, compared to, I can go up to 200 volts for some of my BJTs. And my input impedance is going to be high for these two because they're blocking gates, whereas for my BJTs, those are going to go and have a very low input. We're actually driving current through that input over there. Output impedance is seen as being very low for my IGBTs and for my BJTs, but the output impedance, the actual channel resistance, is high for my MOSFETs. So overall, we see just a really, really good operation of them. Their speed isn't quite the same as my MOSFETs, which are extremely fast because I do have 2 more layers to break over, but they're excellent for most of my usual work. We can get them in small packages for my IGBTs, or we can get them where they're going to be combined together into much larger packages, where I'm actually going to have 3 of them all together. And this is very common, where you're going to go and see them driven together like this, because what this allows us to do is control 3 of them at the same time off of a similar type of waveform, which means we can get 3-phase control. And this is really what we have at the heart of some of our devices, like our variable frequency drives, the VFDs, that are going to chop up. They're going to create a DC. We take AC in, we're going to change it over to high voltage DC, and then we chop it up with one of these to go and create an output. Same with a lot of our light dimmers are going to be IGBT based. Okay, that's as far as we're going to go off of these right now. You'll have a lot of questions when we go to our live session. We'll probably go through some of those calculations again as to how we actually go and see, the amplification through some of these FETs. But it's a lot to cover. There's a lot online for all of this as well, so have at her.